Hello everybody, this is Goran and Eloy from Effective TDs again. And we were just looking at APFs, the basics, and how we create those in Max with TP, and also how we can do that with Houdini. And now we're taking it to the next level, where we want to use these APFs and apply them in a kind of production environment scenario. So basically what I did is I gave Eloy a challenge, which you see on the screen. What you have here is on the left, you have your emitter of particles, and we were just assuming that these particles, they need to get to this side without hitting and colliding with this object. So basically they have to find the way through the maze. Production workflows, I know that this is pretty good use of fields in a 3D world. So why don't you show them how this looks and how we got to that result?
So we have already here the APF created. That's on real time. There is no simulation. Reading from a simulation, it's not flow. Each particle reads the APF that is trying to avoid closest boundaries and finding his path. So we will try to show how to do that with APF, and
Right.
It's a very cool example, I think.
Yeah,
of
I think
APF.
it's pretty cool because you can just do object avoidance with the particles. Don't even have to calculate it. The field calculates it for them in the first frame, and every particle just knows how to avoid objects.
And doesn't matter so much how many particles we have here. So we can see that we can go kind of crazy in number of particles. Since everything is calculated by the APF, you can go higher. Obviously, it takes a little more because each particle needs to find the velocity close by, but not each particle needs to find closest closest normal to objects or
Right.
something like that.
There is no intersecting. There is nothing happens per particle. The particles, all they do is read the velocity direction from the field.
Exactly, and it's what I think the APF it starts to become like really good
Powerful, yeah.
and
It's
powerful.
kind of the way how hybrid fluid solvers work, where you have particles, but they are like the hybrido in real flow, for example.
So yeah, let's go with that. We have our example running. We will turn it off. I will turn off all this and I will explain you what we are doing step by step. So basically, from the previous tutorial, we have the same. We have an APF field here. We create some particles that will follow the APF with an output to. And here we create the field. We have the initiator. It's giving the area of this field. Basically, our field now it's contained on the space that we need, making sure that grabs all our objects. And that's all what we have. So we need to create.
Why don't you first explain them, like how is the method itself working, like the kind of the math behind it? What are we doing?
Okay, basically we will iterate over this APF. So each cell position will grab closest distance to the object. We will take the normal of this object. We will do a cross product with next direction vector. From this, I should paint that because this will.
Yeah, let's paint it.
Let's paint it. So in 3D, we have this is wow, amazing skills. We have our cylinder. We have a cell particle. This cell particle checks the closest point, and it checks the normal of this one. In this one, this will be the normal. We will create, our particles will go on the x direction. We will create cross vector with this x vector. What this will give us is this resulting vector, right, Goran?
That's correct.
Thank you. Will give us this.
So it's
vector.
the normal of the plane that these two vectors create.
Exactly.
Mm-hmm.
Then we will recreate another cross vector between this resulting vector and this normal vector.
Right.
So this will give us now approximately.
So it's a tangent
This.
to the surface, or like almost like a reflection vector that just follows the tangent of the surface.
Exactly. Vector product, what it is you given two vectors will give the third vector that is perpendicular to these two vectors.
Right, to the plane that those two vectors create.
Yes.
Okay, so now we're creating a new direction that follows the surface around those cylinder. And what we also do is we just blend between our original x direction, our incoming kind of velocity, like that's the one, and based on distance to that cylinder, we blend into that resulting double cross vector tangent. So the closer the particle, or the closer the cell to the surface, the more it gets from that tangent. So that way we get like a smooth transition, and particles kind of start already avoiding the object before they even touch it.
Yeah.
Yeah.
We will get something kind of like that.
Exactly, like those arrows.
Yes.
Okay.
So yeah, automatically each shape will always avoid the cylinders.
Yeah.
And at the same time, they will try to follow one main direction.
Right. And just as a side note, I think you are an amazing painter, Eloy.
Thank you.
You could just switch industries and become an artist.
I know. So let's try to do that now. The theory is this one. Let's see how we apply that in TP. Let's start reading these objects. We will need geom helpers for that.
Mm-hmm.
So let's go with a helper, geometry, an object. First we want to load these objects. Will be these cylinders, and also we want the walls.
Mm-hmm.
Doesn't matter how many objects we add here, TP will iterate over all these objects there.
Mm-hmm.
Now we want to have information about these objects. We need to access the normal of these objects. For that, we have to use the geometry particle. Right.
I think so.
Yes.
So that is the normal of the closest point to each cell. Or basically, that gives you the closest point on to each cell first.
Exactly.
Yeah.
We will get, so from each cell, it will give us the closest point on each object.
Yeah.
So we need to read our object array, that is this one, and the position. By the way, this is new in TP 6.6. Before we only had particle. Now we can look for a position. So if you need to offset your particle position to look for something, you can do it.
That is awesome.
And we need to do that on the position wall. So each of these cells will evaluate. So we have position wall, we saw it on the first tutorial. Each of these cells will check for the closest point, is what this does.
Mm-hmm.
And now we want to access the normal, because it's what we need. So we have here the closest point by surface. To read that, we have a geometry geom point that will read all the data that we can find. We can read a lot of things. So we can access the normal.
Can you make the TP window bigger? It's kind of squeezed.
Yeah. We don't need to show, in fact, anything else.
Yeah, just make it full screen.
Yeah, let's go big.
Nice. I like that.
Cool. So, yeah, we want the normal. First thing that we need to do is to create a cross vector from this normal with an x vector.
Mm-hmm.
Let's write this. This will be a point 3, and we want the x vector 1 because we will go in this direction,
right,
left to right. And let's do a cross vector. It's very easy to do that in TP. I don't think that in Houdini it's so easy.
You think so?
Well,
it is a little bit trickier.
I think that you need to write some expression manually for sure. It's all what you need to do on Houdini. But
you would be surprised.
Well, we will see this on the next tutorial. But let's do it here. It's as easy as a math and a math operator. We want to do operations between two vectors. So we will have input to one vector 1 and vector 2. And we will do a vector cross product is all what we need, and we will do it between this vector and our normal.
And just that x vector, that is just in our scene. That x vector could be anything, could be a different vector for each particle. Basically, that is the representation of our main direction that the particle should go, and all the rest is just to avoid the object. So if there would be no obstacle, the particle will always go to that direction that we bring in from that point 3 node.
Right.
Okay, cool.
So now we need our second vector. We create the first a vector. I don't remember if I have. Yeah, this vector, what it does is the cross product between this and this. So we get this vector that I will draw in green. I don't know if it's very visible. Here we go.
Oh my god, this is
Look.
starting to intimidate my drawing skills right now.
I know. So we get this vector.
So that's what we have right now.
Yes.
Okay,
Now
awesome.
we need to go for the blue vector that will be this one. Is what we will do now, the blue vector. To calculate that, we need to do another cross vector, so simply copy that between this vector, yes, this vector, and the normal. Right? So with this, oops, where we are, with this is our green vector, this is the normal, now we get the blue vector. Next, and we can try to plug this into velocity, right?
We can directly do that, yeah. Let's see what happens.
Before that, this will be a very low velocity because it's a vector with a 1 unit. So we will multiply this by some value to make something visible. So let's add another math. We can drag and drop. Now we want to multiply. So our second input will be a float. Vector. When you have a vector and a float, remember to don't switch that. If in TP you create first a float and then a vector, will not work.
Right.
First a vector.
It's just basic math rules. You cannot multiply a float with a vector.
And let's multiply this by 90. So our velocity will be whatever it comes from here, but 90 times bigger. And let's see what we get with that. Nothing, because I need to recalculate. And we
turn this dynamic set off.
That's a good idea to check. No, so we have kind of another problem.
Oh, your x value maybe it's not set.
No, it is objects. So we missed something there. Geom particle.
Oh, you're dividing instead of multiplying.
Oh, good.
You see,
Good
that
catch.
is amazing that it shows right away.
Yeah, this with a math node. Before we will see a math and we will have to check everything. Now it's super easy to see what's going on. So
there you go. You already
again,
see it.
we have on the top view, you can see that the field is created and trying to avoid the cylinders.
Yeah.
But it's inverted.
Well, it's not only inverted. Basically, the particles will always loop around the cylinders as long as they are in the field. Like, because there's no distance fall off that blends to the vector.
That's true.
Right. But this is cool. If you want particles to orbit around objects and follow the surface, this is like a perfect surface follow operator already. So if you had a complex surface, you could just, with this, you could generate a surface follow operator. And the particles would just follow the surface. That makes sense.
But why it's reverse, Goran?
I think you need to switch the second cross vector inputs.
These two?
Yes.
Yes. Let's do it again. Now we have the good direction.
Bam! Look at that.
But we don't have a blend. That is the next step. But as you can see, particles try to avoid the cylinders.
Yeah, they just don't have the blend. So they're kind of keeping the distance to their objects.
So yeah, we will create a blend based on a distance to the closest object, and we will blend between this cross vector and this direction. So when they are far away from any surface, we'll try to go on the X. As soon as they go closer, gradually they will try to avoid the object. So we will create an expression for that. You need an expression mode. We need two vector inputs. One will be A and the other one will be B. We need a value to blend between these two, and will be in a scalar and will be a blend. And then we will have our output that will be a vector, and this output will be a direction. Blend direction, but direction it's fine. The expression that we want to create is 1 minus the blend multiplied by what I did there. 1 minus blend multiplied by A, plus the blend multiplied by p. Goran, this is correct?
It looks like it.
So this should be it.
Right.
Now we want to blend these two vectors before the multiplication. We will blend between this vector and this x vector based on a value to value that we don't have yet. Helper standard value to value. So we want this value to value based on the distance to the surface that we have it here, closest point distance. So we will say in a distance of 15. Do it between 0 and 1. This should be fine.
So basically whatever is 0, avoid, and whatever is 1, keep that original vector.
Yes.
Okay.
So let's see again what we have.
You didn't plug anything.
That's a good catch. It's important to plug things if we want this to be working. And as you can see, this is working.
Already done.
Yes, easy and smooth.
That was amazing.
Now the cool thing is that with the signs we have,
and that was super quick. I mean, that was like,
yes, it takes like
5 minutes.
And explaining everything,
Yeah.
this should take like less than a minute to create from scratch. Now with this curve you can manipulate how these two values blends between. So you can have more defined streams if you want.
Right.
You have full customization with that.
Yeah. So you see they're like stopping before they touch the objects.
Yeah.
And I mean, some of them are still, I think, almost going inside. That is because there's always, until they touch the surface, they don't hit the 0 value of the blend. So it's like, if you would show the wireframe, I don't think we have particles inside, but they kind of touch the surface, right?
Yeah.
Yeah, exactly.
We can go with a higher value on 0.
So they always go to super avoidance before they even touch it.
Oh,
that.
It should be this 0. No?
Yeah, just push it down. Yeah, like
Oh,
this.
yeah, that makes sense.
There you go, look at that.
Oh, well, obviously not like that, but you can create a lot of interesting effects with that. What is happening there?
I think
for some reason
your comma is, yeah, now you go.
For some reason didn't like it. Yeah, now we have it.
But why is it not doing what we expect, Eloy?
That's a good question.
Play it? I think now it does.
Yeah.
Almost.
Almost. Why the blend takes so much? Maybe it's between this distance. Can be also the definition of this field.
Right, how it applies the forces. Huh?
Yeah, we can try to increase the resolution. So if we, instead of 10, we go to 20 or 25 to see more effect, we will have much more points evaluated. So we should have way more definition now. We don't need to have a lot of definitions. It's a cool thing about fields. It will interpolate between. Now we can see the effect.
Now it works properly.
Yes, it was that we don't have enough resolution.
That is pretty sweet.
Yeah. So yeah, this shows kind of the power of APF.
Yeah.
And we can do way much more with that. We can blend.
Actually, could we, instead of the graph?
Yeah.
First of all, why don't we set this to not reset?
Yeah. So let's do it. None.
None.
Yes.
And then instead of this.
Well, none. If you put none, you will need. This will not evaluate the change that you do.
So how do you force it? So
you change it again upper frame.
What if we set here minimum 1? So now it says 0 distance. So okay, so how do we reevaluate?
But now you need to go to reset, to simulation start again. At least it calculates 1 frame. So now you can go to none. Now that it's on memory. So now you will see that it evaluates everything. It's on memory, the APF, so when the simulation reaches the end,
It will just...
it will not need to calculate anything else. It will be immediate. And you will see it now
Awesome.
that it's
It just
super
keeps going.
fast.
Okay, so once you said your field correct, I think it's still not doing exactly what we want. It doesn't, we need to figure out how to get that minimum distance. But yeah, this is amazing. I love how it just like squeezes them here. This is really sweet. All right, this is APFs for crowds.
Yeah, for whatever you want.
Whatever you want. Surface follow. Okay. This is pretty helpful. Thanks so much, Eloy.
No worries. We will see next how to do the same thing in Houdini.
Oh my god. All right. Let's give it a try. See you guys over in the Houdini session.